Last time we proved the linear dependence lemma, which says a dependent list contains a vector that can be removed without changing the span. Today we use that lemma to compare the length of linearly independent lists and spanning lists. Then we finally define bases. Humanity limps forward. Here is the theorem. In a finite-dimensional vector space, every linearly independent list is no longer than every spanning list. So if the independent list has length m, and the spanning list has length n, then m is less than or equal to n. This theorem is the counting engine behind dimension. Yes, even counting apparently needs a legal department. Now the proof. We start with a spanning list, and we insert the independent vectors one at a time. Think of the spanning list as a list of w vectors, and the independent list as a list of u vectors. The w list spans the whole space, so it already reaches everywhere. It may contain useless baggage, because naturally it does. Now insert u1 into the spanning list. Because the W list already spans V, adding U1 creates a dependent list. The linear dependence lemma lets us remove one of the W vectors, not U1, and the list still spans V. Why not remove U1? Because a single non-zero vector in an independent list cannot be the disposable one here. The garbage vector must come from the old spanning list. Then we repeat. Insert U2. Remove another W. Insert U3. Remove another W. Continue this surprisingly bureaucratic exchange. After each step, the list still spans V. We have replaced some old W vectors with independent U vectors. If we ever ran out of W vectors before inserting all the U vectors, we would get a spanning list made only of too few U vectors, contradicting independence. Therefore, there must be at least as many W vectors as U vectors. That proves the theorem. Every linearly independent list has length less than or equal to every spanning list. Here is one consequence I am leaving as an exercise. If U is a subspace of a finite-dimensional vector space V, then U is also finite-dimensional. The hint is to try building a linearly independent list inside U. The theorem you just learned prevents that list from growing forever. See? The theorem is already doing chores. Now we finally define a basis. A basis is a list of vectors that is linearly independent and spans the whole vector space. So a basis has enough vectors to build everything, but not so many that some vector is just standing around collecting notation. For example, the standard coordinate vectors form a basis of R2. Every vector x, y equals x times 1, 0 plus y times 0, 1. But the list 1, 0 and 2, 0 is not a basis. It never leaves the x-axis, which is impressively unhelpful for filling a plane. Here is another proof I am leaving to you. A list is a basis exactly when every vector in V can be written uniquely as a linear combination of that list. The proof is mostly bookkeeping. Span gives existence, and linear independence prevents two different coefficient lists from describing the same vector. Now we prove the next theorem. Every spanning list can be reduced to a basis. Start with a spanning list, move from left to right. Whenever a vector already lies in the span of previous vectors, delete it. If the vector is not in the span of previous vectors, keep it. Very ruthless, very efficient, very unlike most committee meetings. Here is a quick example in R2. Start with the list 1, 2, 3, 6, 4, 7, and 5, 9. The vector 3, 6 is just 3 times 1, 2, so it is redundant and gets deleted. Later, 5, 9 equals 1, 2 plus 4, 7, so it also gets deleted. The remaining list is 1, 2 and 4, 7, which is a basis of R2. Now the proof that this deletion process actually works. First, the remaining list still spans V, because every deleted vector was already built from earlier vectors. Second, the remaining list is linearly independent. If it were dependent, the linear dependence lemma would identify some vector in the span of previous ones. But we deleted all such offenders. So the remaining list spans V and is linearly independent. That is exactly a basis. The corollary is immediate. Every finite-dimensional vector space has a basis. By definition, finite-dimensional means some finite list spans the space. The theorem says that spanning list can be reduced to a basis. Even the zero vector space behaves. Its basis is the empty list. Yes, even nothingness has paperwork. Next time, we move closer to defining dimension properly. We will show that independent lists can be extended to bases, and then prove all bases of the same finite-dimensional space have the same length. After that, dimension is finally well defined. Mathematics has nearly allowed us to count. Try not to get sentimental.